In this video, we are discussing the traveling salesperson problem using approximation algorithm. For that, a graph G is taken with vertex V and edges E. The various vertices are A, B, C, D, E, and the edges are shown in the given graph. These vertices represents different cities, and weights on the edges are indicating the cost to traverse from one city to another in that region. The salesperson has to visit all the cities with minimum cost without visiting a city twice. That is, he will visit all the cities, and that traversal will take minimum cost. However, a person cannot repeat the visiting a city. There are several methods to solve this problem, such as the brute force approach, the branch and bound approach, dynamic programming, heuristic approach, and approximation algorithm. In this video, we are discussing the approximation algorithm to solve the traveling salesman problem. But to understand the difference between the approximation algorithm and other algorithms, we have taken a brute force approach to examine and will compare the performance of both the algorithms. Because the brute force gives the exact minimum value, and the approximation will give a near optimum solution. So we will see at the end how these two results are different. Let's start with the greedy approach. We'll draw the state space tree. Let's say the salesman has started from city A. However, he can start from any of the cities available. So let's say he started from city A. Then from city A, he can go to city B, go to city C, D, and E. To cost of traveling from A to B is 14, that is taken from the graph. A to C is 4, A to D is 10, and A to E is 6. Now, out of all the cities, let's say from A, the salesperson has visited city B. Once he is in B, then he has a choice of moving to city C, moving to city D, or moving to city E. So these are the choices from node B. First of all, we will explore these branches, this leftmost branch first. From B, if he visits C, then cost is 8. If he visits D, cost is 9, and visiting to E is 7. Then when he is in C, he can move to city D, or he can move to city E. If he is in D, he can move to city E, C to D, C to D is cost is. From now, if he is in city E, then he can move to city D. After that, he will return to node A. So once he is in D, he can go to city E, and from E, he can go back to city A. Here is the end of this trip. Then we can backtrack to node E. In E also, there is no other path to explore. We can backtrack to D. From D also, there is no path to explore. We'll go back to node C. From C, I can go to E, and from E, I can go to D. The cost of E to D is 32, and from D, he can return to node A. And D to A cost is 10. So we'll repeat the same process. We will backtrack to D. From D, we'll backtrack to E. From E, we'll backtrack to C. From C, we'll go to B. Then from B, again, we'll explore these branches. So this approach, it is a greedy approach, also known as backtracking approach. And it explores each of the possible paths. Then we compute the cost of every path. For example, from here, we will compute the cost till reaching A. So if I sum up all the values, total equals to 70. Similarly, in this part, path cost is 80. That way it will find the cost of all the paths. We'll see the entire state space tree and we'll compute the cost of each of the branches. So in this diagram, we have explored all the possible paths, and out of that this path gives the minimum cost, which is equals to 45. For that it goes from A to C, from C to E, from E to B, from B to D, and from D to A back. So this cost is 45, which is the best cost, that is exact minimum given by backtracking algorithm. Now we will use approximation algorithm. We'll compare the cost of both the methods. Now we'll be applying the approximation algorithm on the same graph shown in the diagram. There are two methods in approximation to solve the TSP problem: the nearest neighbor approach and the Christoff's algorithm. We'll be using the nearest neighbor technique in order to solve the problem. We can start at any point or any vertex of this graph, and let's say in this case we have considered or we have selected the node A. We'll draw the node A and mark it as visited in the graph. Let's say A is visited. A has 4 paths to go. One from A to B, cost is 14. From A to D, cost is 10. A to E, cost is 8. And A to C, cost is 4. So out of all these 4, the lowest cost is from A to C. So we will draw node C and connect both A and C. This is C. And cost from A to C is marked as 4. Also, we will mark this node as visited. So repeat the process from C. In this case, the edge from C to B has the lowest cost. This cost is 6. Rest of the cost are 9 and 16. But however, from A to C, the cost is 4. But we have already visited A. We cannot go back to A now. That is why we have only one choice. From C to B is the next vertex to visit. We'll connect C and B, and cost is 6. From B, next node we can visit is E because it is the lowest cost with 7. We'll draw E and mark E as visited. Also in the part, we'll put the cost as 7. From E, we have to visit D now because this is only the vertex left out. So we will draw, this is D, and we'll connect E and D. The cost is 32. At D, we have come to an end of this traversal, and now this is the time to return to node A. So we'll connect D and A, and this cost from D to A is 9. So using approximation algorithm, the path followed is from A to C to B to E to D and return to A. Total cost is 4 plus 6 plus 7 plus 32 plus 9, which is equals to 50. So now it is concluded that the approximation algorithm gives only near minimum cost rather than actual minimum. If we compare the backtracking algorithm and the approximation algorithm, backtracking gives by the a cost of 45, whereas this approximation gives a cost of 50. It is not the exact minimum, however, it is a near minimum